Welcome to the next tutorial about our Matlab course. Today we want to extend our existing program so that we can use different intervals for our aggregation in the different programs, and we want to do the second task here so that we get such a nice contour plot or pcolor plot of our motorway data. This is also the last step which we want to do in our project, and the next lessons will improve our programs, because you will see later on, after we're finished today, you will see that it is a little bit bulky and not so nice handleable to run the program. We run things several times. We have, for example, data available in different appearances and things like that. So the next steps for the next lessons will deal with functional programming. Here we will finish now our project, and the rest will improve the things. So let's start with task 1 of today's tutorial, to improve the interval selection so that we have an optional dimension of the aggregation interval. We have to improve all of our aggregation programs, so let's start with the first aggregation without outlier detection. So what we have to replace is this for loop. So therefore I'll keep it. You should not do this in original programs, because everything what you keep will stay there for the rest of the life. But I want to keep it so that you have a complete set of everything what we have done until now. And we copy this because we want to change this for loop. So now let's adapt it. In our case, I want to read the interval size in minutes, or the length of the interval in minutes from the user. So therefore, we have to request the data. So let's create a request with input, and let's request the data. So we write an input, enter length of aggregation interval in minutes, and then we write what we get from the user into this length. If we get wrong values, we keep the user in a while loop. So for example, if it is smaller or equal 0, or if it is greater or equal 1440, because the minutes in one file, or the number of minutes in one file, is the number of minutes of one day, and therefore we have 1440. So therefore, if we have the situation that the user enters something wrong, it will be kept in this request until he enters something correct. And then we have to change this. So what we have to change is this 15 and this 14 here, because we now have to use this new interval. So it's quite simple in case of the 15, because we can directly use this. So in case of the 15, we enter, or we use the iterator, which is the same like what is entered by the user. But now we have to change this. So what do? It's quite simple. We have this, and we're at 14. So therefore we use the interval -1. And the same here. Okay, this should work if, and this is the restriction, if we have intervals which are dividers of 1440, because otherwise the last interval will be a rest, and this will not work. And therefore you can find different solutions. A simple one is you check if you reach the end. So for example, number of time slots is the number of possible time slots, 1440, And if you use this as well here, you are more flexible. But I wanted to show the numbers here so that you understand what happens behind. So numbers minus mean interval. So you calculate always the rest which is still available. And if the rest is larger or equal this, then you can do the normal selection here. Then you can use this. If it is smaller, then you have a rest, and then you should just take the rest. And how do you take the rest? You take the rest if you start at the same position, but instead of having this, you just jump to the end of this line. Because if you have a size larger than this interval length, then you can use this. Otherwise, you take the rest, and then you're in the last interval of this section. So therefore, it should work. Let's add one additional statement here so that we know calculate a mean and prepare this step function. The problem now is that we have to do it for every of our, or for any of our aggregation programs. So we have to do it also for the rest of our aggregation programs where we delete outliers and where we use the Q-mean. So let's do this. Again, we start with the original. So let's continue with the outlier deletion program. So again, we start with the same program like this. We make a copy, and I will keep again what already exists for the 15 minutes interval, so that you have both available. And then we have to change this. We already know how to read the data, so we take this. We do exactly the same. This is what is not so nice, as we always call, for example, here, we call the previous ones, therefore we have to enter it several times. Another possibility would be to start at the beginning, but this is exactly what I meant in the intro, that it is not so nice anymore, because now we have a huge program meanwhile, and therefore it's not so nice anymore to work with a simple script or scripting technique. You have to change things in several things, and you always have to remember which variables exist and which variables you have to create, or you do it like here, so that you have to enter it several times. So, and then we have to do this preparation here. So we have to do the same like here. Let's continue. First of all, again the same. We replace the 15 by this aggregation. And now it's a little bit more difficult, because we have to do the if-else construction here and the if-else construction here. So here it's the same again. We use -1, and also here. So we replace all 14s with the new length of the interval -1. But now again, if we have a divider of 500, for example, which is not a divider for 1440, then we will have a problem, and therefore we have to do here a special condition, and also around here. So the condition is the same, so therefore we request if we have the final interval. So if we deal with the rest, so if it is not the rest, we can do this. If it is the rest, we will have to do a special participating vector, which not goes to the aggregation interval length -1. It must just go until end. And the same we can put around here. So we'll do the same here. And don't forget to set the indent, because otherwise it will be unreadable anywhere. And if it is not the rest element, then we can do this. If it is the rest element, then we do the same, but we will end here in the end. So that's it for the outliers. So let's run it. So again, it requests the file, and then it will run the first without the outlier detection. We have to enter our 500. We already tested this. Then it starts this new loop. We have to enter it again. This is the problem here. So we have to improve this later on. But again, it works. So we have a new figure, and it's again correct in case of this behavior. Now we have to do it for the last aggregation calculation for the Q-mean. We proceed as known. So let's fetch the original Q-mean, and then we'll take this and replace it. I keep it again, and we do exactly the same. So if we run this, we have to enter 3 times the interval, but the rest is the same. So we can replace the 15 here, and we replace the 15 here by this -1, so the 14, I'm sorry, and also the 14 here and here. So if you don't remember anymore how this calculation worked and how the programs were before, then have a look into the videos from the creation of these aggregations. Again, we have the same situation. We have to check if we reached the last interval. So if we did not, then we can calculate this. If we reached, then we have to go just to the end of the interval, so that we take the rest. In this case, we replace this with end, and also here with end, and also here with end. That's it. Let's run the program. So again, we start. Now we have to enter 3 times the interval size. 1 for the aggregation without the outliers, 1 for the aggregation, 1 for the aggregation with the outliers, 1 for the aggregation without the outliers, and 1 for the aggregation with Q-mean. And it works quite well. So now we have a new figure for the Q-mean. It's figure 4. And we have again the same behavior. As bigger the interval, as less difference we have between the different outputs, because the -1s here will not influence the interval too much if it is big. So if a lot of elements participate. So that's it for task 1. The next task is that we want to plot this contour plot, which is our finalization of the pure project. So let's jump back and let's start with an empty script again. We do exactly the same way we did until now. So we call all of the other scripts. If you remember, we had a script which compared the things. This comparison already calculated and plotted all of our mean or aggregations, so that we have 3 different matrices available with the 3 different aggregation outputs, and therefore we can use these. For the run, it will not be so nice, but it works, and we'll get 3 different contour plots like this. And the 3 different contour plots are stated or based on the different aggregation calculations. In the contour plot, you will not see much difference, okay? But let's have a look. So we start with an empty script again. I call it TS contour plot step by step. And we start, of course, with clear all, close all, and CLC. And then we call our comparison program, because it will prepare all of our previous calculations. And then we write what we want to do now. So we create a contour plot. An additional thing what we need is the distances. So if you remember that, I move this plot to here. So if you remember that we have on the x-axis we have the time, and on the y-axis we have the distance to Munich, then we need this distance. So you can take it directly from the Excel table. Later on in the project, if we improve all of these things, we'll do this, because there's always one column in the Excel table which represents the distance or the length of the section. And if you sum up, if you have a sum of these sections, so that section 1 plus section 2, and then section 1, section 2, section 3 lengths, and then so on, you will get the chainage of all of these lengths, and then you will get these distances starting from Munich, which is 0, to the direction to Nuremberg. So therefore, for a simplification at this point, I will improve it, or I will just do it in the way that I create the chainage manually. So it's just the sum. This is section 1 has 0, and this is distant, or is section length 1 plus 2. Section length 1, then section length 1 plus 2, and so on. Okay. So, and now we have to plot 3 different plots. I remember, and this is again what is not so nice here, that the last plot here was given by this number 3. It's with outlier. This is the problem, because you have to always remember. This is the Q-mean, which is the last one. So it's plot number 4. And then we have the other plots, the comparison and things like that. So I remember that the last plot was plot number 5. And therefore I plot now from the figure number 6 to 8. And this is what I meant. You always have to remember what you already created to avoid overriding. This is also not so nice. So in an improvement which we start next week, or which we do for next week, we will improve these things. Okay, and then we know that we had in the comparison the TS aggregation, TS aggregation outlier, because we ran through all of these things, and we did things several times, of course, because we did not store it somewhere. And we have to now plot if it is figure 6, we plot this. If it is figure 7, we plot this. If it is figure 8, we plot this. And therefore we can use again a switch case statement. I can go through this quite fast because you should already know this. And we create a new intermediate matrix which contains the individual setting here. So we always do now this. And we create a new matrix. So it's, if it is 7, we do this. And if it is 8, we do this. So we have now a new matrix with the individual aggregation according to the figure number. And then we can plot the individual output. So what is content of this? Content of this is our step function. So we will have several times the same number. For the contour plot, we don't need this. So for the contour plot, it would be enough to select only the real aggregated or the real mean values. And therefore, we extract the mean matrix. We extract just the means from here to avoid the step view also in the contour plot. So we extract all lines and just take each first element of the individual interval length. So we take this interval length which we entered before. Here's another critical situation if you use different interval length, for example. So if you enter when you requested 3 times the different numbers, then you will have here a problem. Therefore, it's also not so nice. But I just want to show you a straightforward programming situation so that you sit down and you program a script. And then you will see the difference later on in the next lesson to a real software suite where you have a very adaptable, without changes in the program, adaptable software suite based on functions. Of course, we have now also the situation that we have different time steps. For example, we have to prepare the time, which is the x-axis. And therefore, if you do this in the original program, it would be quite simple. You just do time steps equal, and then you start from 0. In the first step, you start from 0. Then you have interval length of 15, which is 15 over 60 as an iterator, and you end up 15 minutes before a complete day is over, because you start with 0, and then the last interval starts at 15 minutes before the 0 o'clock, 24 hour. So therefore, this would be the simple version if you don't have this aggregated interval length. And I show you a simple calculation for that. Iterative calculations are not so nice, but I do it anyway here because we have no floating point numbers, and then it works. If you have floating point numbers, you should not do this. So what I do is I always sum up the next partition. So for example, I calculate the size and I divide the 24 hours by the size, and I always add up in a for loop the individual interval length, so that the first time is 0, the next time is 0 plus the individual length of the interval, and so on. And I create time steps with this new calculated or iteratively calculated interval. So if you do this with floating point numbers, then it happens that you will have round errors or rounding errors, which make a lot of problems. Okay, next step, we will create the figure. So now let's plot it. So we want to plot the contour plot, and then we create the individual figure according to this figure number 6, 7, and 8. Contour plot, or what we do is better said a color plot, can be done with pcolor. There you need an x-axis, you need a y-axis, and you need a matrix of the size of x and y, which contains the third dimension, which is then represented with a color. So therefore we have the mean, which we took from here. We have the time steps, which we calculated according to our individual aggregation time, and we use the chainage, which we set up here manually, or which you can iteratively create from the raw data in the Excel table. And with this, we'll have the color plot. So let's run the program until now here, so that you see the output. Let's run it. You will see that we will have to enter several times the different entries. So let's take 5 minutes, for example. And then it starts the program again, and it will do the calculation again. Aggregation without outliers and aggregation with outliers. And it starts the program again. Do you remember we did the comparison and we did it in this way? And this is what is not so nice in our straightforward programming. If you spend more time for an intelligent solution, then you will avoid this. And directly working with functions would solve this problem. So if we watch now the output, or one of the outputs, it looks like this. It's a little bit different to what we expected. I can compare it. So it should be something like this. What we have is that we have these lines for the x and y positions, and we have not the smooth shaping here. So we have each individual interval has a unique color, and therefore we have no smooth shaping. And therefore we have to improve this. We also want that the congestions, I mean situations which are slow traffic, should be shown in red, and situations which are fast traffic should be blue. Therefore we have to change also the coloring of that. So let's improve this. That we don't have to enter all the stuff again, I will do the following. I'll change this so that we don't call it all the time. We just do the plotting anymore. So let's first of all create the right coloring. Colors in Matlab are represented with a special way of color tables. It means that you have the red, green, blue channels. So you have a three-dimensional matrix where you have 255 or 256, starting from 0, ending with 1.0 elements in the rows, and 3 columns. And the first column is the red, next column is the blue, third column is the red, green, blue, the red, green, and blue. And the number gives you the intention of this color. So therefore you can optimize these things. If you watch the output, so what we got as an output, you can see that it's almost like this what we want. So we have red or yellow colors for the slow traffic and blue colors for the red and yellow colors for the fast traffic and blue for the slow traffic. And therefore, if we just turn it, if we just take the existing color map or the color description as it is, and we just flip it or turn it, then it might directly work. So let's do this. If I just go to figure 7, I select this figure, and if I directly just flip the color map, so I take the chat color map and assign it to the new, then you directly see that it works nicely. So now we have the blue regions are the fast traffic, the red regions are the slow traffic. So what did I do? I created a color map as it is standard, so with 256 elements. It's called a chat color map, and then I just flip it here. So you don't see it, sorry, I have to switch myself off. So I create a color map with 256 elements, and then I just flip it so that the bottom is so up to down, and then I set the color map of my graph again with this new color map which I flipped, and then it will show like this. So this is what we have to do here for each output. And let's also comment it that we changed the color map. You can set each individual color map you want, but this works quite nicely. And then we want to improve the shaping, and we want to set a horizontal color bar. So let's write a comment improve the look, and then we do two different things which you find in the help pages. One is the shading, which is a shading of interpolated modes, so that you don't have this, let's say, step function of colors. You have now really a nice smooth interpolated color change. And we want to set a horizontal color bar so that you see what does a red color mean and what does a blue color mean. And then we set a title, we set the X label, and we also want to set the background of the image or the background of the window to white. This can be done again. Here we have to set the individual figure number. So we can select the figure number, and then we select it with attributes. You already know this from other lessons, color to white. So we set the color bar, we give a title, we write the Y label, the X label, and we set the background to white. So let's run the program. And you see it directly changes. So you have now this nice smoothing effect. You just see the differences. You also see some shockwave scenarios and things like that, or you see very beautiful here the speed limits, things like that. What we get are 3 different graphs with 3 different aggregations. And here we see that there's just small changes. For example, here at this scenario, you see that there are differences here. For example, also here in this scenario. So there are slight differences. There are things like this -1 here. What do you see? So that you have, with the outliers, you have artifacts. Without the outliers is much better. But with the Q-weighted mean, it's a smooth behavior, or it's more smooth like the other. Okay, so what else do we want? That we have a better interpretation of where we are in the distance. We want to set lines at each single sensor. So therefore, we want to set entry and exit infos and also sensor infos. How can we do this? So I want to show you the sample again. So if I shift this here, then this should be the result. And therefore, why did we set it to white? If you don't do this, if you don't set the background to white, then you have this text in front of gray, which is not so nice. It's better readable if you have white. Therefore, the background is set to white. And then we want to have horizontal lines, and we always draw a line with the line function, and we start with x1, x2. So x1 is the starting point of the x-axis, x2 is the end point of the x-axis, and then we start with y1, y2, and y1, y2 is exactly the sensor distance, so coming from the chainage. So at each point of the chainage, we want to set a line. So therefore, we have to first of all create the x-axis. So the x-axis part is created quite simple because it's the starting point of the x-axis and the end point of the x-axis. And we do the same for the y, but for the y we have to have differences. We have to use the chainage part. So therefore we run through the chainage. Which is done like this. So we have a line count, and we run through the chainage, and then we create the y1 and y2 in the following style, that we take the distance from the chainage, and we use for y1 and y2 the same because we have horizontal lines, and then we just plot it with the line function. So we use line x and y. The x comes from here, the y comes from here, and then it's color, and we plot it with k. So it means black. You remember, blue is B, and black would be also B, but therefore they selected the K. So with this, if we do this, and if I show you the graphs, so if I do this, it will change the last graph. Okay, so let's run the program, and you see how it looks like. And now we want to write the text of the exit points. You have to watch the project description for that. In the project description, the very first video about, you will see a diagram of the sensor positions and also how the exit and entry points are named. And this is the only part which must be done manually, or you cannot create a loop, or you keep the names in a special cell matrix. I do it in a very simple way. I use the text function from Matlab. Text function sets text in a plot, and then you have to define the x and y position of the text, and then you can set special attributes. So the special attributes are the font size. I use font size 8, and also the color K. And for the position, I use the x-axis, the end of the x-axis, plus a little bit, so that we are outside here, and I will use the positions of the exit point. So in 15 kilometers, there's the first exit point, and so on, or there's the last exit point. And therefore, you do this for all of the exit points manually here, and you will get directly, if you run it in each plot, you will directly get the position of the exit points. So, and that's it. So if you run the whole program, you can individually select the interval size. You will get 3 outputs. You will see differences. As larger the intervals, as less artifacts you will see, as less of these shock waves or lines, diagonals you will see, where you see the propagation of traffic situations, of stopping scenarios, and therefore we finished all of our project parts. Now you can discuss things. For example, you can identify some speed limits or temporary speed limits, things like that. Okay. Okay, so let's switch back to our task sheet, and then we finished everything. So you can use this program, but you have to do several changes, manual changes of the program, manual, let's say, adaptations like what we did, comment out so that not all things are operated all the time, things like that. You see that things are done several times, and this is not really a helpful thing. And therefore, we now want to improve our program. So we want to improve the program in the style that we now have a possibility to directly use functions. So functions are quite helpful because, do you remember from the Christmas programming, they keep a local memory. So things like that your workspace is full of elements, and that you always have to remember what was the name of this thing, is not necessary anymore. So you write now function for read, for XLS read, for the save, for the load, and for the read table, and they return always the same things which you require later on. You have everything already available in your scripts. Then you do the plotting. It's a function for the plotting. Then you do the aggregation, so you convert the three programs. In principle, you just have to copy and paste things in a special style into the function. So the first task is nothing more than copy and paste. Not really, but you have to think about what you need and which arguments you need and which return parameters you want. And then you do all of the aggregations, and you do the contour plot, and you do the comparison. So task 1 is copy and paste everything what you have now. So you have now an idea what you need. You got a feeling. So you learned a lot during the work. You learned a lot how to do things, how to improve things. So now you can train it, because now you just convert it into functions. And then task 2 is you take the functions and you write one main program. So what we did until now is you had a program, and the program called the other program, and this program called the other program, and this program, and so on. So that if you started the last program like this contour plot, then all of the other programs are operated. They are started in sequence, so that you got all of the data and all of the things. It was not so flexible. You saw you had to enter things several times. It was not so flexible. You had to do commenting out of the calls if you wanted to do things several times, and things like that. So what we now want, not this nasty way, we want to have one main program. It's of course also possible with scripts to do this, but with the scripts you have to always remember how the names are in the scripts of the different individual matrices, for example. And what we want to do now is we have one main program, and in the main program you define the names, and the names inside of the function are totally different. So you don't have to take care what the function does. So the function was created in task 1. You just take a main program, which is a sequence of the function calls with the individual menus. So you ask, like what we did, do you want to read the data with load? Do you want to read the data with XLS read, with read table, things like that? You ask this with a menu, and then you do the next step and the next step. You can ask, do you want to plot the data, and so on. Therefore, you're quite flexible. You keep always the terminology, always the name, the nomenclature in one package. So we don't shift the whole stuff through different programs. We keep it in the main program, and therefore you can write the main very flexible, and you don't have to take care on the different function. And this is what you should do in task 2. This is the main task. This is just copy and paste. This is a little bit of work, I know, but this is the main task. And the rest, the next lessons, we'll just focus on the improvement of text reading. So if we have everything, we can extend our reading method with a real text reading method, so that we not have to do some assumptions, what we did with load and save. We can directly read the text, tab separated text from the Excel file. So this is the plan for the final lessons, and therefore next task is this. So stay safe, and we'll see each other again in the next tutorial.